Okay, last video, I hope. All right, so we looked at this in class on some of the examples that we tried doing, where you have events that are independent of each other, and then we have events that are dependent on each other. So let's talk about these. So events are independent if the occurrence of either of them does not affect the probability that the other occurs. So for example, classic example, I flip a coin and I roll a die. This coin couldn't care less what the die is doing. Totally independent of each other. Also, if I roll two dice, whatever happens on here is not going to affect what happens on here. Okay, so those are independent. So when something happens here, it does not affect what happens on the other one. Those are independent events. So some examples of independent events would be flipping multiple coins, okay, or another example, rolling multiple dice. Okay, this can also mean rolling the same dice many times. If I roll a 6 and I roll a 3 and I roll a 6 and I roll a 1 and I roll a 3, does the die keep track of what I've been rolling? Does it care that I already rolled a 6 before? Is it not going to give me another 6 because I just rolled a 6? Look at that. I just rolled a 1 like 3 times. Okay, so no. So these are independent events. Each time I roll the die, it doesn't care what happened before. It doesn't care what's going to happen next. It's completely independent of any other rolling of the die. Okay, those are independent events. So if we have independent events, and I am a winner if two things happen, okay, so A and B, then you can just multiply the probability of A times the probability of B, okay? So this can be extended to any number of things. So say flipping a coin. So flip a coin. Flip a coin 3 times. So I can take the probability of, let's see, what do we want to get? Flip a coin 3 times and get 3 heads. Okay, I want to get heads each time. So that would be the probability of heads, heads, heads. I want to get heads 3 times in a row. I want all 3 of those to happen. Okay, so I can say that's the same thing as getting probability of heads times probability of heads times probability of heads. So probability of heads is 1 out of 2 times 1 out of 2 times 1 out of 2, because each time I have a 1 out of 2 chance. So what's the chance of getting heads 3 times in a row? That would be equal to 1 times 1 times 1 is 1, 2 times 2 times 2 is 8, 1 out of 8. Okay, and we can prove that by making a list of all the things that could happen, or by making a tree diagram. So you can see we can prove this by making a tree diagram. So first flip, I could get heads or I could get tails. Second flip, so here comes the second flip, I could get heads or tails. Or if I had already had a tail, I could get heads or tails. And then third, I'm running out of room. Third, I could get heads or tails again, or off of here, heads, tails, or heads, tails, heads, tails. So I'm only going to be a winner if I get heads all 3 times. So if I look at all my possible outcomes here, my possible outcomes, the first one is heads, heads, heads. The next one is heads, heads, tails. The next one is heads, tails, heads. And then heads, tails, tails. And then tails, heads, heads. And then tails, heads, tails. And then tails, tails, heads. And lastly, tails, tails, tails. So how many possible outcomes? 1, 2, 3, 4, 5, 6, 7, 8. There's 8 possible ways that I could flip 3 coins, 8 possible outcomes. And how many of them are heads, heads, heads? Only 1. So, which is equal to 1 out of 8. I don't like where I put that. Let me put my answer up here. easier to see when it's on the white paper, equals 1 out of 8. Okay, so here it is, doing it just by using the rule of multiplication. Okay, and this is when you have an and problem. And how do we say and? We use, no, it's not on here. So I could have written this as probability of heads and heads and heads. Okay, there's another way of writing it. Could have written it like that as well. Oftentimes, though, we simplify it and just write it like that. Okay, so I have a 1 out of 8 chance of getting heads 3 times in a row. Okay, so that's an example of an independent event. So each time I flip the coin, it doesn't care what happened before. It doesn't care that I already got a heads. The second time I flip it, it could still give me heads or tails. And again, doesn't care if I did heads twice in a row. The third time, it still could give me heads or tails. It's equally likely that that's still going to happen. All right, so those are independent events. Now, what are dependent events? We've talked about dependent events in class when we talked about having a bag of marbles, and we're pulling things out of the bag of marbles. And I, of course, did not have any marbles. Instead, I just had like a collection of stuff. Okay, so here I have a bag of stuff. Some of them are red, some of them are blue. Dependent events means that when I do one thing, it's going to affect the chance of something else happening. So, for example, if I choose 2 objects from this collection of items, if I choose a red object, the first time I choose a red object, there's 5 things in the bag. So I have, a chance out of 5. But once I remove that, now my chance is out of 4. So we have to take into account that the first event is actually impacting what's going to happen next. Because if I remove this, I don't have 5 things to choose from anymore. Okay, so this is what we mean by dependent events. The first event affects the second event. Okay, events are dependent if the occurrence of one of the events does affect the occurrence of the other event. So if A and B are dependent, then we have this slightly fancier notation, which I am going to give you an example of. Okay, so here is my example. So I want to select 2 students from a class. So selecting 2 students from a class of 10. Okay, I'm going to select 2 students out of a class of 10. Okay, in my class, there are 4 seniors. Find the probability of selecting 2 seniors. By the way, this is still theoretical probability. I'm assuming that it's equally likely. Each student has an equal likeliness of being selected. Okay, so no bias is involved. Okay, so selecting 2 students from a class of 10. So the first student, my first student, how many choices do I have? I have 10, so I have 10 students to choose from. How many of them are seniors? 4 of them are seniors. Okay, since I'm interested in selecting 2 seniors, we have to assume that I've now selected a senior. So now for my second selection, how many seniors do I have left? Well, I already selected 1, so now I only have 3 seniors. And out of how many students? I already took out 1 student, so now there's only 9 students left. And then we multiply the results together. 4 times 3 is 12. 10 times 9 is 90. And there's our probability of selecting 2 seniors. So notice on this one, once I've taken 1 senior out of the mix, that affects the number of seniors that are left. It also affects the number of students that are left. So these are dependent. These are dependent events. The first event actually affects the second event. Oftentimes you'll get asked a question, what if two people are selected at the same time? How would you figure out the probability of selecting two seniors? You actually do it the same way. We never say that I'm going to select two things simultaneously. I'm never going to just like, because as soon as this one has been selected, the second one has a slightly different probability, okay, than if I had selected this one first. So we don't worry about them happening simultaneously. We just say one happens and then the other happens. We don't worry about, oh, what if they happen at exactly the same time? Okay, so we always say, well, one's going to happen and then the other's going to happen. All right, so those are dependent events. And that's it. We finally finished the note. Sorry I talk so slow.